Welcome to the Deep Dive. Today we're tackling a heavy topic, one that looms large in our collective consciousness. The potential for a nuclear holocaust, nuclear Armageddon, whatever name you give it. It's something we need to understand clearly.
Absolutely. And our goal here isn't just to rehash the familiar images of mushroom clouds. We need to go deeper, look at what the science tells us about the global aftermath. We're talking widespread destruction, yes, but also radioactive fallout, maybe nuclear winter, famine, EMP, potentially the end of civilization as we know it.
Right, so we'll unpack those specific mechanisms, the firestorms, the pulse effect, radiation sickness, and definitely nuclear winter, which really shifted how people thought about this whole thing.
And underpinning all of this is that Cold War concept, mutually assured destruction, or MAD. It's this paradox, This immense threat has arguably kept a certain kind of peace, but it's a peace held under a constant shadow. The science trying to model this threat is what drives policy and anti-nuclear movements.
Okay, let's start with the term itself, Holocaust. Using it for nuclear war has huge weight, but the idea of atomic destruction as a fiery end, well, that actually showed up in fiction surprisingly early.
It did. The word comes from the Greek holocaustos, meaning completely burnt. Originally a religious term, but Reginald Glossop used it in his 1926 novel, The Orphan of Space.
1926? That's, wow, almost 20 years before the first atomic bomb.
Exactly. He described an atomic strike on Moscow, calling it this Holocaust. It shows the concept, the fear was already there. And importantly, the term's use has broadened. Activists talk about nuclear testing as genocide, ecocide, even nuclear colonialism, considering the impact on specific communities and environments.
It carries a heavy load. Now, fast forward to today. What are we looking at in terms of actual weapons, the arsenal?
Well, as of 2021, the number was around 13,410 nuclear weapons globally. Now, that's way down from the peak Cold War numbers, which were just astronomical.
Thousands upon thousands more back then.
Right. But even with fewer weapons overall, thousands are still deployed, and many are on what's called hair trigger alert, ready to launch in minutes.
And here's the twist, right? Fewer weapons, but the risk isn't necessarily lower because of this modernization paradox everyone's talking about.
That's the crucial point. It's not just fewer weapons. Every single country with nuclear weapons is currently modernizing its arsenal.
So new delivery systems, maybe smaller warheads, stealthier tech.
Precisely. Faster missiles, hypersonic capabilities, things that are harder to detect. And this modernization, ironically, might be making things more dangerous.
How so?
It shrinks. The time leaders have to decide if an attack warning is real or a false alarm. If weapons are faster and stealthier, the pressure to launch on warning, before your own weapons are destroyed, increases dramatically. It potentially makes accidental escalation more likely.
And that plays into the doomsday clock, doesn't it? That symbolic clock moving closer to midnight?
It absolutely reflects that heightened risk perception among experts. It hit 100 seconds to midnight in 2020, then 90 seconds in 2023, and just recently, 89 seconds in 2025.
89 seconds.
Yeah. The Bulletin of the Atomic Scientists explicitly cites this modernization race and ongoing global instability as the key reasons.
But, some might argue, are we really closer to doomsday than during the Cold War peak? Are the numbers down, but the politics just feel worse?
It's a fair question. The old MAD framework between the U.S. and the Soviet Union, while terrifying, did create a kind of stability. The sheer size of the arsenals made large-scale war unthinkable, suicidal.
Right.
But that stability might be eroding. Modernization is one factor. The other is proliferation. More countries getting these weapons.
So MAD worked maybe for two giants, but what happens with multiple smaller nuclear powers?
Well, this system gets a lot messier, less predictable, and many scientists now think a regional nuclear war, say, between India and Pakistan or other pair of nations, is actually more likely than a full U.S.-Russia exchange.
And the terrifying part is, even a small regional war could have global consequences, right? Because of those secondary effects we mentioned.
Exactly. That's the critical shift in understanding. Even a limited exchange can trigger global climate effects, like nuclear winter.
Before we dive into those effects, let's touch on historical likelihood. The Cuban Missile Crisis is always the go-to example of how close we came.
It really is the benchmark. Kennedy himself reportedly estimated the odds of it escalating to nuclear war is somewhere between 1 in 3 and 50-50. A coin toss, essentially.
It's chilling. And what about current expert views on the risks, say, this century?
There was a poll back in 2008 from the Future of Humanity Institute. The median expert estimate was about a 1% chance of complete human extinction from nuclear war this century.
1% doesn't sound huge, but for extinction.
It's existentially significant, and they estimated a 10% chance of a nuclear catastrophe killing at least 1 billion people. Again, these aren't predictions, but they show experts still see this as a very real, ongoing risk.
Okay, let's transition to the aftermath itself. First, the immediate, more localized effects people focused on before the nuclear winter models came along. What did Cold War estimates look like?
Right, pre-winter thinking. There was a major study in 1979 for the U.S. Senate. It looked at a full-scale exchange between the U.S. and the Soviet Union, hitting both military targets and cities.
And the projected casualties.
They estimated anywhere from 35% to 77% of the U.S. population killed and 20% to 40% of the Soviet population. Hundreds of millions dead just from the blasts, the fires, the immediate radiation.
Unimaginable numbers, but you're saying even those horrific figures were incomplete.
They were, because they mainly accounted for the direct effects, the blast, the fire, the prompt radiation, and maybe some very early economic disruption. They didn't fully factor in the long-term killers.
Like a mechanism A in nuclear fallout.
Exactly. Fallout is the radioactive dust and ash created by the explosion, especially ground bursts, that gets thrown way up into the atmosphere.
And we have real-world data on this from atmospheric testing, don't we? The bomb pulse.
We do. All that testing in the 50s and early 60s spread radioactive material globally. The peak was around 1963. Even though those weren't weapons used in anger, estimates suggest that fallout caused maybe 2.4 million extra cancer deaths worldwide over the following decades. It's why the Partial Test Ban Treaty happened.
So in a real war scenario, what makes fallout so dangerous for survivors?
It's a mix of radioactive isotopes. Some decay quickly, causing intense radiation hazards nearby, sometimes falling as black rain mixed with soot. But the longer-term danger comes from specific isotopes getting into the environment and the food chain.
Which ones are the main concerns?
Strontium-90 and cesium-137 are big ones. They have longer half-lives, meaning they stick around. Strontium-90 acts like calcium, so your body can absorb it into bones, irradiating you from the inside for years. These can create radioactive hotspots, making areas unsafe for potentially 5 years or more.
And the immediate health effects for those exposed. Acute radiation sickness sounds truly dreadful.
It is. It's a spectrum. Acute radiation syndrome, or ARS. It starts with nausea, vomiting the prodromal phase. Higher doses damage bone marrow, wiping out your immune system, leading to infections, bleeding, death within weeks.
And the highest doses.
Central nervous system damage, seizures, coma, death within days. It's brutal. And even if you survive the acute phase, you've got long-term cancer risks, potential birth defects if exposed in utero, even possible genetic damage passed down generations.
Okay, so fallout is the slow poisoning killer. Let's talk about the other immediate threat, the silent one, electromagnetic pulse, EMP.
Right, NEMP, the nuclear electromagnetic pulse. This is a massive burst of electromagnetic energy, particularly from a high-altitude detonation, maybe hundreds of kilometers up.
Why high altitude?
Detonating high up maximizes the area covered on the Earth's curved surface. A single large weapon detonated over the central U.S. could potentially affect the entire continent.
And what does it do?
It induces huge, instantaneous voltage spikes in long conductors, power lines, communication cables, antennas. This surge can fry unprotected electronics. Think about our modern world.
Everything relies on electronics. Hospitals, water pumps, food refrigeration, communication networks.
All potentially crippled. Instantly. And that leads to the recovery problem. Normally, if a local grid fails, help comes from outside. Repair crews, replacement parts.
But with a continental-scale EMP,
there is no outside help. Everyone's grid is down simultaneously. Replacing massive custom-built power transformers takes months, even years, under normal circumstances. After an EMP, it could be practically impossible on a large scale. Industrial society could just stop.
That sounds utterly apocalyptic, but there's some debate about how likely or severe this EMP threat really is, isn't there?
There is. You have groups like the EMP Commission, figures like James Woolsey, arguing it's the biggest threat, that even a small state could potentially cripple the U.S. with a single high-altitude burst. They push hard for grid hardening.
And the counter-argument.
Others, sometimes writing in places like Physics Today, argue the risk might be overstated. They question if a rogue state could reliably achieve the perfect detonation. They point out that some infrastructure, like buried cables, has inherent shielding, and that we already monitor for natural solar storms, which can cause similar, though perhaps less intense, effects.
So The reality is likely complex. The vulnerability is real, but the exact scale of the disaster is debated.
Exactly. It's a significant threat, but maybe not the absolute certainty sometimes portrayed.
Okay, so those are the more immediate, localized, or infrastructure level effects. But the real game changer in understanding the global risk was the development of nuclear winter theory.
Absolutely. This shifted everything. The idea is that nuclear explosions, especially over cities, would ignite massive firestorms. Think burning wood, plastics, asphalt, oil, huge amounts of fuel.
And the intense heat from these fires does something crucial to the smoke and soot.
It lofts it incredibly high, not just into the lower atmosphere of the troposphere, where rain would wash out relatively quickly. It injects potentially millions, even hundreds of millions, of tons of black carbon soot directly into the stratosphere.
Above the weather system.
Right. And up there, this fine black soot can stay suspended for years, spreading globally. It acts like a massive shroud, blocking sunlight from reaching the surface.
This was first seriously modeled by the TTIPS team, Turco, Toon, Ackerman, Pollack, Sagan back in 1983. That's where the term nuclear winter came from. What do the more sophisticated modern climate models show now?
The picture is still grim, maybe even grimmer in some ways because the effects last longer than first thought. A full-scale war, say US-Russia, could drop average global surface temperatures by 7 to 8 degrees Celsius, that's about 13 to 15 Fahrenheit, for several years.
A huge global change. But it wouldn't be uniform, would it?
No, and that's critical. The major agricultural regions of the Northern Hemisphere, the U.S. breadbasket, Europe, Russia, China, could see cooling of 12 to 20 degrees Celsius during the summer growing seasons. Some continental interiors, like parts of Russia, might see temperatures plummet by 35 degrees C.
Basically eliminating agriculture through freezing temperatures, even in summer.
Yes. And the models now suggest this cooling effect could persist for over a decade because the soot is so high up, above the rain. Plus, global precipitation could decrease by around 45%, so it's colder and drier.
So back in the 80s, they estimated mass starvation if food production stopped for a year. But these new models suggest the shutdown lasts much, much longer.
That's the frightening update. The models indicate a period of no food production extending for many years, making the resulting famine far worse and longer lasting than initially conceived.
And this brings us back to the regional conflict point. You don't need a full US-Russia war to trigger this nightmare.
No, you don't. That's maybe the most crucial finding of recent research. Take a scenario like India and Pakistan, using, say, 50 Hiroshima-sized bombs each on cities. That's only 100 relatively small weapons in total.
Small compared to the thousands in major arsenals.
Right. But even that limited exchange is estimated to release about 5 million tons of soot into the stratosphere.
Is 5 million tons enough to cause global winter?
It's enough to cause significant multi-year cooling, especially across North America and Eurasia, the key grain belts. Models show it would likely lead to widespread crop failures and famine. Researchers call the potential consequences of even this small war catastrophic on a global scale.
And there's another layer to this. Ozone damage.
Yes. That same soot, heated by absorbing sunlight in the stratosphere, messes with atmospheric chemistry. It changes wind patterns and pulls in nitrogen oxides that destroy the ozone layer.
So on top of cold and dark, survivors would face increased UV radiation.
Exactly. A regional conflict could potentially create a near-global ozone hole lasting a decade or more.
Yay.
That means dangerous UV levels harming humans, ecosystems, and any agriculture that might somehow survive the cold.
Cold, drought, darkness, UV radiation, collapsing distribution systems. It becomes clear why the main killer in most scenarios isn't the blast, it's famine.
Nuclear famine. That's projected to be the deadliest consequence by far. Groups like the International Physicians for the Prevention of Nuclear War, IPPNW, have estimated that even that India-Pakistan regional scenario could put over 2 billion people at risk of starvation.
2 billion, a third of humanity potentially from a limited war.
And the numbers for a full U.S.-Russia exchange are almost incomprehensible. A 2022 study in Nature Food projected 360 million direct deaths from blasts and fire, but over 5 billion deaths from starvation due to the climate disruption.
5 billion, you just let that sink in. The study suggested something like 99% death rates in the US, Europe, Russia, China in that scenario.
Yes. Essentially, near total annihilation in the major Northern Hemisphere population centers, primarily through starvation over the years following the war. When the initial nuclear winter studies came out, it was a profound shock. The realization that the ultimate threat wasn't just destruction, but global starvation.
Okay, billions dead from famine, civilization collapsed. But what about total human extinction, the only cockroaches survive idea? Is that
Well,
plausible?
it was certainly feared during the Cold War, but current science suggests total human extinction is very unlikely. Devastation, yes. Billions dead, yes. But some parts of the world, probably in the southern hemisphere, would likely remain technically habitable, though life would be incredibly harsh and primitive. The risk isn't zero, but absolute extinction is considered improbable.
What's the evidence against total extinction?
There's a book from 1988, Would the Insects Inherit the Earth, by Philip Dolan. He looked at the aftermath of the huge hydrogen bomb tests at Bikini and Enitak atolls. These were island ecosystems subjected to massive destruction. And the local ecosystems, while initially obliterated, did eventually recover. It showed that life, particularly microbial life, insects, plants, is incredibly resilient. It argued against the idea that all complex life would vanish. Human civilization would end, certainly, but biological extinction is a much higher bar.
Now, if we are talking about deliberate attempts at total extinction, we have to mention the hypothetical cobalt bomb.
Ah, yes, Leo Szilard's warning from the 1950s. The idea is chillingly straightforward. Take a large hydrogen bomb and encase it in ordinary cobalt metal.
And the explosion makes the cobalt radioactive.
Intensely radioactive. The neutrons from the H-bomb transmute the stable cobalt into cobalt-60. Cobalt-60 has a half-life of about 5 years.
Long enough to spread globally, short enough to be intensely radioactive.
Exactly. It could potentially blanket the planet in lethal radiation for years, making the surface uninhabitable for humans and other complex life. A true doomsday weapon.
Was there any strategic rationale proposed, other than pure terror?
Szilard suggested it could be seen as horribly efficient. You wouldn't need lots of expensive missiles. Just a few massive bombs, possibly automated, detonated perhaps by a ship or even pre-placed, designed purely to guarantee total annihilation as the ultimate deterrent.
Is there any limitation? Would one bomb do it?
Likely not. Because atmospheric circulation between the northern and southern hemispheres is somewhat limited, you'd probably need to detonate devices in both hemispheres to ensure truly global, inescapable fallout coverage.
Let's step back from hypothetical doomsday devices to the real arsenals. We used to hear about overkill having enough weapons to destroy the world multiple times over.
Yeah, that phrase got traction, often attributed to figures like Philip Noel Baker in the 70s, killing mankind 3 or 4, 10 times over. But analysts like Brian Martin pointed out this was often based on flawed logic. It often came from just scaling up the effects of Hiroshima, like assuming a bomb 1,000 times bigger kills 1,000 times more people. But destruction doesn't scale linearly like that. The area of destruction increases much more slowly than the yield. You hit diminishing returns quickly, you can't kill more people than exist, and you can't destroy the same city twice.
So overkill in terms of blast damage was maybe exaggerated, but the global winter effect means even smaller arsenals can cause global catastrophe.
Precisely. The real overkill potential comes from the atmospheric effects, not just stacking up blast radii. Though, to contextualize the raw power, World War II involved about 3 megatons total explosive yield. The peak Cold War arsenal was around 13,000 megatons.
Equivalent to thousands of World War II.
Yes, a staggering amount of energy. But even that is dwarfed by some natural events.
Like supervolcanoes.
Right. Mount Tambora in 1815, maybe 30,000 megatons. It caused the year without a summer. Mount Toba, 74,000 years ago, perhaps 20 million megatons. That likely caused a massive human population bottleneck.
So why is comparing nuclear war to a supervolcano misleading if the energy can be comparable or even less?
Because the type of atmospheric injection is different, and potentially more dangerous in the nuclear case. Supervolcanoes throw up massive amounts of sulfur dioxide, which forms reflective sulfate aerosols, causing cooling. But nuclear firestorms inject black carbon soot high into the stratosphere.
And soot absorbs sunlight, heating the stratosphere.
Exactly. That heating is key to the prolonged duration of nuclear winter and the associated ozone destruction. Volcanoes cause cooling, but the mechanism and duration are different. Also, practically speaking, detonating thousands of nuclear weapons simultaneously across the globe is hard due to nuclear fratricide, earlier explosions interfering with later ones.
This all brings us to the sheer moral weight of this risk. Philosopher Derek Parfit had a stark thought experiment about this.
He did. He asked us to compare 3 scenarios. 1, peace. 2, a nuclear war killing 99% of humanity. 3, a nuclear war killing 100% extinction. Parfit argued that the moral difference between 99% dead and 100% dead is actually greater than the difference between peace and 99% dead.
Why is that final 1% so critical, morally speaking?
Because 100% death means the end of all future human potential. All the lives, discoveries, art experiences that could ever happen, gone forever. 99% dead is an unimaginable catastrophe, but it leaves a sliver of hope for recovery, for the continuation of humanity's story. Extinction closes the book permanently.
Which leads to a powerful conclusion about our responsibility.
Right. Philosopher Nick Bostrom argues that because the stakes involve not just us, but potentially trillions of future lives, we have an overwhelming moral duty to reduce even small probabilities of human extinction. Any risk, however tiny, demands our utmost attention because the potential loss is infinite.
The weight of all possible futures resting on avoiding that final step.
Precisely.
So, to wrap up this deep dive, the unavoidable takeaway seems to be that the core threat isn't just the bomb itself anymore. It's the chain reaction. The soot from burning cities causing nuclear winter, triggering global famine that kills billions, potentially coupled with infrastructure collapse from EMP, and crucially, even regional conflicts now pose a global existential threat.
And that leads to a final thought, something grounded in the history of how we even learned about these effects. The understanding of nuclear winter and famine, the very things that make these weapons truly existential threats on a planetary scale, came after the major arms buildup of the Cold War. We built tens of thousands of these weapons before fully grasping their ultimate consequence. So the question for you, the listener, is, what other catastrophic long-term secondary effects might our current science still be missing about the weapons we possess right now? What don't we know yet?
A sobering question indeed. Thank you for sharing your sources and joining us for this deep dive. We'll see you next time.
Welcome back to the deep dive. Okay, I want you to start us off today by just closing your eyes for a second.
Unless you're driving, of course.
Yes, please. If you're driving, keep your eyes on the road. But for everyone else, just for a moment, conjure up an image of Pegasus. What's the very first thing that pops into your head?
Oh, I can almost guarantee what they're seeing. It's white, it's pristine.
Totally pristine.
It's got these beautiful, perfect feathered wings, and it's probably, frolicking in a field of flowers.
Exactly. It's the logo on the side of a moving van, or maybe on a vintage lunchbox with some, pastel sparkles around it.
The My Little Pony version.
It is the My Little Pony version. It's sanitized, it's safe. But today, we're taking the source material, this massive, incredibly detailed breakdown of the history, the archaeology, the linguistics.
Everything.
And we're going to completely shatter that lunchbox image.
We really are. It's a radical deconstruction we've got ahead of us.
It is.
Because if you actually look at the ancient texts, the pottery, the etymology, Pegasus isn't a pet.
Not at all.
He's a monster born from a beheading. He's a living weapon of mass destruction for the king of the gods. He's the ancient equivalent of a stealth bomber.
That is the mission for today.
Yeah.
We're going to trace this entire arc from the blood-soaked beaches of his birth,
Right,
all the way to the shoulder patches of British paratroopers dropping into Normandy in World War II. It is a wild ride.
It spans thousands of years. And I think the thing that's going to surprise people the most is the central tension in the myth itself.
This duality you mentioned.
Exactly, this duality. Is Pegasus a creature of water, a creator of gentle springs, or is he a creature of the storm, a bearer of lightning?
That's the debate we have to get into. And to do that, we have to start in the only place that makes any sense.
The origin story.
The origin story. And I have to warn you, this isn't like Disney violent. This is Game of Thrones violent.
Oh, it is visceral. It really is. To understand Pegasus, you first have to look at the family tree, which is
Complicated.
complicated. It's doing a lot of heavy lifting there, yeah.
Okay, so let's start with the father. The source material points to Poseidon. Now, usually we think guy with the trident controls the ocean.
Right. Standard stuff. But we have to peel back some layers of Greek theology here. In the archaic Greek tradition, Poseidon's portfolio was much bigger than just the sea. He was the Hippios.
The horse god. I thought he was the earth shaker.
He's both. The Greeks actually associated the pounding of horses' hooves with the rumbling of the earth with earthquakes.
Oh, okay, that makes sense.
There are myths where Poseidon literally creates the first horse. He has this deep elemental connection to equines. So genetically, if you can even apply genetics to gods,
Ah, right.
the horse part of Pegasus comes directly from Dad.
Okay, so we've got the horse god father, now for the mother. And this is where the record scratch happens for a lot of people.
Mm-hmm.
We're talking about Medusa.
The Gorgon.
Yeah.
Yeah.
Before she was a monster, she was a woman. But
Yeah.
But in the version of the story where Pegasus comes into play, she is fully in her snakes for hair, turn you to stone era.
Correct. She's a Solonic monster, a creature of the earth and the underworld. And the mechanics of this birth they're unique in mythology.
How so?
Well, usually, even with monsters, there's a gestation or an egg or some kind of labor. Not here.
No.
The sources are very, very specific. Pegasus was foaled at the exact moment of Medusa's death.
And this is the famous scene with Perseus, right? The hero with the mirrored shield.
That's the one. Perseus sneaks in, uses the reflection to avoid her gaze, and
slice off her head.
exactly. And the text says that as the head was severed, Pegasus and his brother Chrysaor sprang forth.
Wait, they jumped out of her neck.
That's version A, and it is by far the most metal version. They sprang directly from the blood jetting from her severed neck.
Yeah.
It's a kind of birth by release. The idea is that they were trapped inside her, maybe because of Poseidon's influence, and the sword is what finally freed them.
That is incredibly graphic. It almost
Yeah.
reminds me of how Athena was born from Zeus's head, fully armored.
Yeah.
But this is way messier.
So much messier. This is a fountain of gore. It links creation directly to destruction. You kill the monster, and from that violence, beauty and terror emerges.
Okay, so that's version A. What are the other theories?
Well, version B is a bit more grounded, you could say. It suggests the blood from her neck spilled onto the earth,
Okay.
and the earth, fertilized by that divine but monstrous blood, birthed the horses.
That feels very Mother Earth archetype, like the soil itself is reacting to this horrible event.
It does. And then you have version C, which I personally find the most poetic and maybe the most thematically relevant for our conversation.
Go on.
It says Pegasus was formed from a mixture of Medusa's blood, the pain of her death, and the sea foam from the waves crashing nearby.
Blood, pain, and sea foam.
Oh,
Wow, that captures the duality right there, doesn't it?
it really does.
The sea foam links directly back to Poseidon. And it kind of mirrors the birth of Aphrodite, who was also born from sea foam after. Well, another pretty violent incident involving Uranus.
Greeks loved paralleling beauty with violence. Aphrodite is beauty born of violence. Pegasus is power born of violence. But we can't skip over the brother.
Right. Everyone forgets the brother.
Chrysaor, the forgotten twin.
The forgotten twin.
Born at the exact same second, twins. But while Pegasus is a winged stallion,
Chrysaor is a dude.
almost always depicted as a human warrior, yeah. Sometimes a giant.
Yeah.
And he's holding a golden sword.
Talk about non-identical twins, a flying horse and a guy with a sword. Family reunions must have been awkward.
It just highlights that Medusa was this conduit for chaos. She produced two completely different aspects of power.
So you've got the warrior on the ground.
That's Chrysaor and the power of the sky.
That's Pegasus. They represent the two domains of war. So we've got this blood-soaked foal standing on a beach next to his giant brother. Now we have to name him. And this is where our deep dive gets really interesting, because the name Pegasus might be the biggest red herring in history.
Oh, it's a classic case. It's folk etymology versus what you might call linguistic archaeology.
Meaning?
The ancient Greeks, specifically the poet Hesiod, who's one of our main sources for all this, he looked at the name and thought, this sounds Greek.
They sort of reverse engineered it. They tried to make it fit their own dictionary.
Exactly. They saw the word Pegasus,
Right.
and they connected it to the Greek word pagae,
Pagae.
which means spring or, well,
Which, it fits the story, right? He was born near the springs of Oceanus, this mythical river that circles the world.
it's a very convenient narrative. It makes him a water spirit. And for centuries, that was the accepted truth. He's the horse of the water.
Okay.
But modern linguists have looked at the region where these myths first came from, Anatolia, which is modern-day Turkey, and found something that completely upends that whole theory.
This is the Luwian connection. I love this part.
Right. So Luwian was an Indo-European language spoken in Western Anatolia way back in the Bronze Age. And in Luwian, there's a word, Pegasus.
And I'm guessing that doesn't mean water.
Not even close. It means lightning.
Pegasus. Pegasus. Wow, you can actually hear the shift.
It's a clear phonetic match, and it gets even better.
Ow.
In that Luwian culture, there was a weather god, a storm deity, whose title was Pegasus.
No way.
And this deity was often represented by a bull, or, you guessed it, a horse carrying lightning bolts.
So if you accept this theory, Pegasus isn't a Greek water horse at all. He's an immigrant.
He is.
He's a storm god from Turkey that the Greeks adopted and sort of rebranded.
Precisely. He is the lightning. And when you view him through that lens, his entire career path suddenly makes so much more sense.
Right. Why does he end up carrying Zeus's thunderbolts?
Because that's who he always was. He's living electricity.
That is a massive paradigm shift. It takes him from being a magical animal to being a force of nature. It's like finding out that, I don't know, Santa Claus was originally a warrior god of snow or something. But the Greeks didn't fully abandon the water connection, did they? They kept the spring aspect in his mythology.
They hybridized it. That's the beauty of mythology. Nothing is ever truly deleted. It's just layered over.
Right.
So you have this creature who is secretly a storm god, but in the Greek stories, he acts as a kind of dowsing rod for water.
A dowsing rod.
The myth says that wherever Pegasus struck his hoof to the earth, a fresh spring would burst forth.
So he's a ground pounder, he strikes the earth, and water responds.
The most famous example of this is the Hippocrene.
The one on Mount Helicon.
The mountain of the Muses, yes. And the backstory here, which was recorded by Antoninus Liberalis, is hilarious and frankly bizarre.
Let's hear it.
The Muses began to sing a song. Now, these are the goddesses of inspiration, so this wasn't just a nice little tune. This was the ultimate song.
Okay.
And it was so beautiful, so incredibly moving, that the mountain itself went into a state of rapture.
Wait, the mountain started vibing.
It started swelling. It was literally rising up toward the sky, expanding with the joy of the music. It was losing its grounding.
That is a psychedelic image. The geology is reacting to the playlist.
Yeah.
The mountain's getting too hyped.
Exactly. Poseidon saw this chaos unfolding and realized the mountain was going to burst or just float away into the heavens. It was unnatural. So he basically radioed Pegasus, metaphorically,
Right.
and said, go fix it. Pegasus flew down and just stomped on the mountain with his hoof.
A kinetic impact. He didn't ask it to stop. He hit it.
He kicked the mountain back down to earth.
Yeah.
He deflated the ego of the rock. And from that impact crater, the Hippocrene spring gushed out.
The horse spring.
So the water is a byproduct of his power. It wasn't about him being gentle. It was about him exerting force to restore order. He's a creature that corrects the landscape.
I love that. Even his most peaceful acts are actually acts of violence. He stomped a mountain into submission. But let's pivot back to the storm side of him. Because while he's making springs on the ground, the archaeology shows he was definitely viewed as a sky creature by the people who mattered.
By the state, you mean?
Yeah.
The Romi are the smoking gun here. If you look at the A signatum,
What are those?
there are these heavy bronze currency bars from early Rome. Imagine, like, a brick of bronze that you used to buy things.
Not exactly pocket change.
Definitely not. And on these bars, you see the depiction so clearly. On one side, you have Pegasus,
And on the other,
an eagle holding a thunderbolt.
they're paired, like heads and tails on a coin.
They are two sides of divine authority. The eagle is the avatar of Jupiter, or Zeus, and Pegasus is the delivery system. The ancients understood that Pegasus wasn't just a horse. He was the carrier of the weapon.
He's the B-52 bomber carrying the payload.
Precisely. Which brings us to the one human who looked at this lightning-carrying, mountain-stomping monster and thought,
I bet I can ride that.
Bellerophon?
This is the tragedy of the myth, really. Bellerophon is a classic hero, but he's not a demigod like Hercules. He doesn't have super strengths.
He's just a guy. A very, very ambitious guy from Corinth.
And he can't just go out and catch this thing.
No. The texts are clear. You cannot tame Pegasus with strength. He's wild, divine energy. If you try to lasso him, you die. If you try to wrestle him, you die.
So what does he do?
He knew this, or at least he was advised of it by a seer. So he went to the experts. He engaged in a ritual called incubation.
That sounds like a startup term, but in ancient Greece it meant something very specific, didn't it?
It did. You would go and sleep in the sanctuary of a god. In this case, it was the temple of Athena, hoping that the deity would visit your dreams and give you a solution.
It's like divine tech support.
It is. You're essentially hacking the system by asking the admin for a cheat code.
And Athena actually shows up.
She does. She appears in his dream, and she leaves a physical object beside him for when he wakes up.
The golden bridle.
A golden bridle. And this is fascinating because a bridle is a piece of technology. It's a tool of control.
Right. Athena is the goddess of wisdom and strategy. She's not giving him a weapon, like a sword. She's giving him the interface.
That's a brilliant way to put it. The bridle is the interface between human will and divine power. Without it, the connection is impossible.
So he takes the bridle.
He takes this golden bridle, finds Pegasus drinking at the Pierian spring, and just slips it on. And the text says, Pegasus yielded immediately. The wildness was tamed by the technology of the gods.
So now he has the ultimate war machine. And he doesn't use it to, deliver mail.
He goes hunting.
He goes after the chimera.
The chimera.
Let's describe this thing, because chimera is another one of those words that's kind of lost its punch. We think of it as just a mix of things. But the original beast was a nightmare.
A total biological abomination. It had a lion's head, a goat's body protruding from its back.
In the middle of its back, yeah.
And a venomous snake for a tail.
So it's biting you from the front and the back at the same time.
And the key feature, it breathed fire. It was a walking flamethrower.
So if you're a guy with a sword on the ground, you're dead. You can't get close.
You're toast, literally.
The range of the fire breath is longer than your spear.
Exactly. And this is where Pegasus changes the nature of warfare in the myth. Bellerophon realizes he has a three-dimensional advantage. He takes to the sky.
Air superiority. He invents the airstrike.
It is the first recorded instance of close air support in mythology. And the pottery, specifically these Laconian Kylix cups, they show Bellerophon hovering directly above the chimera.
Smart.
He stays out of the range of the fire breath and just rains down arrows or spear thrusts from above.
It's a drone strike.
Yeah.
He's using the horse to completely negate the enemy's primary advantage. He's hacking combat.
And it works. He kills the unkillable beast because he changed the battlefield. He won because of Pegasus. But here's the problem. When you ride the lightning, eventually it goes to your head. Bellerophon starts believing his own press clippings.
Hubris. The classic Greek flaw. Bellerophon decides that because he can do what gods do, kill monsters, fly through the sky, he must be a god.
Or at least he deserves to live with them.
So he tries to fly Pegasus to Mount Olympus. He tries to crash the VIP lounge of the universe.
He literally flies up and tries to knock on the front door, and Zeus is not having it. The gods are very protective of their boundaries.
So what happens?
The myth says Zeus sent a gadfly, a tiny stinging insect, to bite Pegasus.
That's such a petty move by Zeus. He could have thrown a thunderbolt, but he used a fly.
It's efficient. And it's so ironic. The great beast that killed the chimera is undone by a tiny little bug.
So the fly bites the horse.
Pegasus bucks in surprise, and Bellerophon he loses his grip.
And this is the crucial moment of separation. Bellerophon falls.
He tumbles thousands of feet, crashing into a thorn bush, ending up blinded and crippled, wandering the earth alone. It's a miserable end for him.
But Pegasus
doesn't fall.
The horse keeps going.
He sheds the rider. The human weight, the human ego, that was the problem. Once Bellerophon is gone, Pegasus continues his ascent. He flies right into the gates of Olympus.
He got the promotion.
He absolutely did. He was welcomed into the stalls of Zeus, and this is where he steps into his true role, the role that matches that old Luwian name, Pegasus.
He becomes the bearer of the thunderbolt. I want to picture this. He's not just like grazing in a field. He's on call. He's in the armory.
He is on duty. The sources say he worked alongside two other entities, Astrepe and Bronte.
Lightning and thunder.
They were goddesses, the personifications of the storm. So you have the flash, which is Astrath, the sound, which is Bronte, and the carrier,
which is Pegasus. It's a tactical team.
It was. Whenever Zeus wanted to smite someone, Pegasus was the delivery vehicle. He carried the missiles.
It's just incredible consistency. From the blood of the Gorgon to the storm god of Anatolia to the arsenal of Zeus, he is always associated with this terrifying, powerful energy.
He is never just a horse.
And for this service.
Because he was faithful. Because he didn't have the ego of Bellerophon. He was rewarded. He was given a catasterism.
Define that for us.
It's the process of becoming a star, of turning into a constellation. Zeus placed him in the night sky.
And there's a beautiful, almost cinematic detail in the text about this moment.
Yes. It's said that as Pegasus ascended to the stars, a single feather fell from his wing.
Just one.
It drifted down through the atmosphere and landed near the city of Tarsus.
It's such a melancholy image. The beast is gone, but a piece of him remains on Earth.
And Tarsus was a major city in Cilicia, again, leaking right back to that Anatolian region. It ties the myth geographically back to its roots.
And it comes full circle.
It does. In the Indo-European tradition, the rising of the Pegasus constellation was the sign of spring. So the storm brings the rain brings the spring.
So that's the ancient history. And if the story just ended there, it would be a top-tier myth. But it doesn't end.
Not at all.
This symbol, this lightning horse, it goes dormant for a while, survives the Dark Ages, and then pops up in the most unexpected place.
The British Army. It's one of the most successful brand revivals in history. We're fast-forwarding to 1941. Britain is in the thick of World War II.
Right. The Nazis have conquered Europe, technology is changing everything, and the British realize they need a new kind of soldier.
They can't just march across France anymore.
They need airborne troops, paratroopers, men who could jump out of planes behind enemy lines. This was a brand new concept.
So they're forming the airborne forces, and they need an insignia, something that just screams elite, fast, and death from above.
They needed a Bellerophon.
We needed a Bellerophon, exactly. They looked at the history books, and they chose the image of Bellerophon riding Pegasus.
I mean, it is literally perfect. A warrior arriving at the battle by air. It's not just a cool picture, it's a mission statement.
The design is iconic. It's a light blue Bellerophon and Pegasus on a maroon background.
And that maroon background is really significant.
It is. That patch is the reason the British Airborne and many airborne units around the world today wear the maroon beret.
The Red Devils.
The Germans called them the Rote Teufel, the Red Devils, because of that beret color, but the patch came first.
But there's a bit of a mystery about who actually drew this patch, isn't there? It wasn't just some marketing agency.
No, it's a bit of a whodunit. The romantic theory points to Daphne du Maurier.
The novelist. The woman who wrote Rebecca and the Birds.
The very same. She was married to General Frederick Boy Browning, who was essentially the father of the British Airborne.
So the story goes she came up with it.
The story goes that she suggested the design, or maybe sketched it out for him over dinner one night. I love the idea of a Gothic horror novelist designing a military patch.
It adds a certain gravitas to it, doesn't it?
It adds a literary flair. But if we're being strict and look at the British Army's official records, they credit Major Edward Seago.
Huh?
He was a landscape painter from East Anglia who was serving in the military. They say he designed it in May of 1942.
So whoever drew it, it worked. It became a rallying cry. And it wasn't just a patch on a sleeve. It became a geographic reality on D-Day.
The night of June 5th, 1944. This is the absolute tip of the spear for the invasion of Normandy.
The objective was the bridge over the Caen Canal.
A vital strategic point. If the Germans held it, they could send tanks to crush the landings at Sword Beat.
But if the British blew it up, they couldn't advance inland.
They had to capture it intact. A huge challenge.
And they didn't parachute in for this one.
No, this was a glider operation, which is, frankly, even more insane.
How so?
They flew these silent, unpowered wooden gliders. They were essentially plywood boxes full of soldiers in the middle of the night.
And they landed. How close?
They landed within meters of the bridge. The pilot, Staff Sergeant Walwork, basically put the glider's nose right into the barbed wire defenses. It was a crash landing assault.
That's the 6th Airborne Division.
They stormed the bridge, overwhelmed the German garrison in about 10 minutes, and held it against counterattacks until reinforcements arrived from the beaches.
An absolutely textbook operation.
It was, and in honor of that unit and the patch they all wore.
The French renamed the bridge.
It's still known today as Pegasus Bridge. There's a museum there. It's a pilgrimage site for military historians.
It just gives me chills. You have this creature born from the blood of a Gorgon in 700 BC. And 2,500 years later, there's a bridge in France named after him because a bunch of guys in maroon berets dropped from the sky to fight fascism.
It just shows the enduring power of the archetype. The symbol didn't change its meaning. The technology just finally caught up to the myth.
That's a great way to put it.
Bellerophon needed a magical horse to attack from the air. The British needed gliders and C-47 transport planes. But the spirit of it, the vertical envelopment, it's identical.
And it's not just the military. Once you start looking for Pegasus, you see him everywhere. He has just infiltrated our culture.
He really has. He's a favorite of the corporate world. If you drove around on the mid-20th century, you saw the red Pegasus of Mobil Oil everywhere.
A flying red horse on every corner.
It represented power, speed, engine performance, that internal combustion energy. They were basically saying, put this gas in your car and your car will fly.
And movies, too. If you grew up in the 90s, the TriStar Pictures logo.
Oh, yeah. The white horse running across the screen, wings unfolding right at the end. It captures the magic of cinema, the idea that imagination can take flight.
Even entire regions have adopted him. Tuscany in Italy.
Yes. If you look at the flag of Tuscany, it's a silver Pegasus on a white or sometimes red field.
What's the connection there? Is it Etruscan or?
It actually traces back to the Renaissance. The artist Benvenuto Cellini made a famous medal in 1537 depicting Pegasus. But the modern usage comes from World War II again.
Really?
The Tuscan Committee of National Liberation, the local resistance against the Nazis, they adopted the Pegasus as their symbol of freedom.
So again, it becomes a symbol of fighting back,
Right.
of resistance, rising above.
It resonated with that idea of rising above the occupation.
We even sent him to space.
We did. The Ecuadorian Space Agency launched a satellite named Pegaso in 2013. It was their very first satellite.
How did that go? Did it reach Olympus?
Well, it had a bit of a Bellerophon moment, unfortunately. It made it to orbit. It was broadcasting the Ecuadorian anthem, and then it was struck by debris from an old Russian rocket body.
Space chunk. The gadfly of orbit.
Essentially, it spun out of control and went silent. A story of high-tech hubris meeting a high-velocity reality.
Poor Pegaso. But it still proves the point. We look at that winged horse and we see the future. We see the beyond. We see something that can take us higher than we're supposed to go.
We do. Absolutely.
So we've unpacked all these layers. We've gone from Medusa's neck to the stars, from ancient springs to Normandy gliders. What's the big takeaway here? When the listener sees that winged horse next time, what should they be thinking?
I think they have to remember the duality. It's so easy to just see the spring, the pretty poetic horse.
Like the lunchbox version?
But the history, the linguistics, the warfare, it all tells us he is fire, he is Pegasus, he is the lightning.
He is power.
He's raw, kinetic energy. He can be beautiful, yes, but he's also dangerous. He serves the king of the gods. He carries the weapons. He stomps mountains.
And he carries paratroopers.
Exactly. He's the symbol of capability, the ability to go where others cannot, and to strike with incredible power when you get there.
It definitely changes the vibe of that lunchbox.
Significantly.
I want to leave you with a challenge. After this, I want you to look up 2 images. First, Google A's Signetum Pegasus. Look at that clunky, heavy bronze bar from ancient Rome. Look at the muscle on that horse. And then look up Pegasus Bridge, 1944. Look at the wrecked gliders and connect those 2 dots in your mind. See that straight line of history connecting them.
It's a powerful visual exercise.
Thanks for diving deep with us today. We'll see you in the next one. Stay curious.
Welcome back to the Deep Dive. It is great to have you with us. Today we are wrestling with a ghost. We're talking about something that is effectively everything, and yet for us here on Earth, it's frustratingly close to being nothing. We are unpacking the ultimate paradox of the periodic table.
That is the perfect way to frame it.
Yeah.
Yeah. It's the element of contradictions. We are looking at an element that makes up, what, roughly 75% of all normal matter in the universe?
75%.
It's the fuel of the stars, the simplest chemical structure possible. And yet, here on Earth, it's elusive, it's difficult to catch, it's a nightmare to store, and for the last century, we've mostly had to manufacture it ourselves using pretty dirty methods.
Exactly. It's the most abundant thing out there, but if I want a tank of it, I have to go through this massive industrial process to get it. We're talking, of course, about hydrogen. Symbol H, atomic number 1, the OG element.
The OG element is a very fitting description. It really is the starting point of chemistry.
And the mission for this deep dive is, well, it's pretty massive. We want to unpack how this single proton-electron duo, which formed shortly after the Big Bang, is currently trying to revolutionize our energy grid. It's literally feeding the entire human population, and it's giving engineers massive headaches because of its weird quantum behaviors.
It's a journey from the birth of the cosmos to the inside of a fuel cell in a modern bus. And along the way, we have to deal with invisible fires and metals that turn to dust.
I have to say, one of the things that stuck out to me in the research, and I just can't get this out of my head, is the idea that water, the stuff we drink every day, is basically just hydrogen ash.
That's
What's left over after hydrogen burns.
That is a very dramatic but chemically accurate way to put it. When hydrogen burns, it reacts with oxygen. The energy releases the fire, and the exhaust, the residue, is H2O.
So water is just exhaust.
Water is the exhaust of hydrogen combustion. But I prefer to frame it as the fundamental building block. If you understand hydrogen, you really start to understand the architecture of the universe itself.
Okay, let's unpack this. Before we get to the rocket ships and the green energy revolution, we have to go back, way back. Not just to the Big Bang, but to the humans who first realized this gas was actually a thing. Because for a long time, we didn't even know it existed. Right?
We didn't.
Yeah.
Which is strange considering how reactive it is. If you look at the history and etymology, the name itself tells a story. Hydrogen comes from the ancient Greek. Hudur, meaning water, and genaj, meaning I bring forth or I create.
So literally water former.
Exactly, water former. But that name didn't come until much later. The discovery timeline is really a comedy of errors. You have to go back to 1671. Robert Boyle, the famous chemist, is in his lab.
Okay.
He drops some iron filings into dilute acids.
A classic chemistry set experiment. You see bubbles.
Right. And he sees bubbles. He sees this gas coming off. But he doesn't realize he's discovered a new element. He just describes the reaction. He misses the significance that this gas is flammable. He essentially sees the smoke but misses the fire.
So he sees it and notes it down and just moves on. When do we actually realize, hey, this is a distinct substance?
That takes nearly another 100 years. 1766. Henry Cavendish. Now, Cavendish is a fascinating character in the history of science. He was incredibly wealthy, painfully shy likely on the autism spectrum by modern standards, and an absolute genius. He isolates this gas, and he calls it inflammable air.
Inflammable air. Catchy.
And here's where it gets really interesting and, slightly ironic. Cavendish was a believer in the phlogiston theory.
Oh, phlogiston. That was the hypothetical substance that people thought existed inside things to make them burn, right? Like wood had phlogiston in it and burning just released it.
Precisely. It was a completely wrong theory, but it was the scientific consensus of the time. Cavendish speculated that this inflammable air he found was actually pure phlogiston. He thought he had isolated the essence of fire itself.
So he discovers the most fundamental element in the universe, and his conclusion is, I found the magic fire ghost particle.
Essentially, yes. But he did notice something crucial. When he burned this inflammable air, it produced dew.
Water.
Water.
Which shouldn't happen if it was just fire stuff. Fire shouldn't turn into water.
Exactly. And that is where Antoine Lavoisier comes in. In 1783, he reproduces Cavendish's experiment. He realizes that this gas isn't phlogiston. It is a unique element that, when combined with oxygen, creates water. So he gives it the name hydrogen.
Water former.
Water former.
And once we knew what it was, we started using it pretty quickly.
We did. That same year, 1783, we see the first hydrogen balloons.
Right.
By 1806, we have the first internal combustion engine running on hydrogen-oxygen mixture.
Wait, 1806? We had hydrogen engines before we had gasoline engines.
We did. The Derivaze engine. It wasn't very practical, but the concept was there. Hydrogen has been an energy carrier for a very, very long time.
But obviously the early usage hits a major snag. We can't talk about hydrogen history without talking about the big floating elephant in the room.
The airships.
The airships.
The Zeppelins. Hydrogen is the lightest element, so it provides incredible lift. It's only about 7% the density of air. For decades, it was the standard for lighter-than-air travel. But as we know, hydrogen is highly flammable.
And that leads us, of course, to the Hindenburg disaster in 1937.
Which effectively ended the era of the hydrogen airship. It caused a massive shift toward helium, which is non-flammable, but much rarer and more expensive. It's a classic case of safety overriding utility. We chose the heavier, more expensive gas because we didn't want to explode.
So we have this element that we identified, named, used to float around, and then realized was incredibly explosive. But let's zoom out, like way out. You mentioned earlier that this is 75% of the universe.
That's right. If you count by mass, it's 75%. If you count by the sheer number of atoms, it's more like 90%.
That is mind-boggling. Where did it all come from?
It is the primordial element. In the chronology of the universe, protons formed within the first second after the Big Bang. But neutral hydrogen atoms, where an electron is actually bound to a proton, they formed about 370,000 years later.
370,000 years seems like a long time to wait for the first atom.
In cosmic terms, it's a blink of an eye. This period is called the recombination epoch. The universe expanded and cooled just enough for that plasma to settle down into atoms. And from those clouds of hydrogen, gravity started to pull them together to form stars.
So stars are basically just massive hydrogen-burning furnaces.
Fusion furnaces, yes. They fuse hydrogen into helium, releasing massive amounts of energy. That's sunlight hitting your face right now. That is the result of hydrogen fusion 93 million miles away.
Okay, so it's in the stars, it's in the interstellar medium, but what about closer to home? What about in our own solar system? I saw something in the notes about Jupiter that sounded like, well, science fiction.
Ah, yes, metallic hydrogen.
Metallic hydrogen. That sounds like a heavy metal band, but what is it actually?
It is a state of matter that we can barely comprehend on Earth. Deep inside giant planets like Jupiter, the pressure is unimaginable. We're talking about 400 million pascals of pressure.
And what does that do to the gas?
It squeezes the hydrogen atoms so tightly together that they behave like a metal. The electrons become delocalized, meaning they can flow freely through the structure. So inside Jupiter, hydrogen conducts electricity. It creates this massive magnetic field.
So if I could survive the pressure, which I obviously couldn't, I would be looking at a sea of liquid metal hydrogen.
Essentially, it's a mind-bending concept.
Yeah.
But on Earth, the story is very different.
Right, because if I go outside and take a deep breath, I'm not inhaling much hydrogen, am I?
Very, very little. It's present in the atmosphere at about 0.5 parts per million.
That's basically nothing. So why is it so rare here if it's so common everywhere else?
Gravity. Hydrogen is just too light. Earth's gravity isn't strong enough to hold onto it in its gaseous form, H2. Over billions of years, most of the free hydrogen gas simply floated up to the top of the atmosphere and escaped into space.
It just drifted away.
It did. So on Earth, hydrogen is almost exclusively found in compounds. It's locked up in water, H2O, and it's locked up in hydrocarbons, fossil fuels. To get hydrogen here, we have to break those bonds. We have to liberate it.
Okay, so we've established it's the Houdini of elements. It escapes Earth. It changes states inside Jupiter. But when we do capture it, it gets even weirder. I want to talk about this quantum weirdness section because this blew my mind. Hydrogen isn't just hydrogen.
No, it is not. This is a detail that often gets overlooked in basic chemistry, but it is absolutely critical for anyone trying to work with liquid hydrogen. We're talking about spin isomers.
Spin isomers. Okay, lay it on us.
So hydrogen molecule, H2, has 2 protons in the nuclei. Protons have a quantum property called spin. You can think of them like little spinning tops.
Okay, I'm picturing 2 spinning tops.
Yeah, there are 2 ways these spins can align. If the 2 protons are spinning in the same direction, parallel. We call that orthohydrogen.
Ortho, same direction, got it.
If they're spinning in opposite directions, anti-parallel. We call that parahydrogen.
Para, opposite. Okay, why does this matter? Who cares which way the protons are spinning?
The universe cares because they have different energy levels. Orthohydrogen has more energy. At room temperature, hydrogen gas is about 75% ortho and 25% para.
Okay, so normal gas is mostly ortho.
Right. But here is the catch. The why this matters moment. Orthohydrogen is unstable at low temperatures. If you cool hydrogen down to turn it into a liquid, which you have to do at minus 253 degrees Celsius.
Which is incredibly cold.
Incredibly cold. When you do that, the orthohydrogen naturally wants to convert into parahydrogen.
Okay, so it changes its spin. What's the big deal?
The conversion releases heat. It is exothermic.
Wait, so you cool it down to make it a liquid.
Yeah.
And then it spontaneously releases heat.
Precisely. And the amount of heat released by that conversion is actually greater than the heat of vaporization of liquid hydrogen.
So if I just cool it down and put it in a tank?
The conversion heat will boil the liquid hydrogen away.
No.
You spend all this energy liquefying it, and then it boils itself off from the inside out because of quantum spin flipping.
That is incredibly frustrating. It's like the element is actively fighting you.
It is. That is why in industrial liquefaction, they have to use special catalysts like ferric oxide during the cooling process. These catalysts force the conversion from ortho to para while it is being cooled, so the heat can be removed by the refrigerator. If you don't do that, you lose your fuel.
That is a wild level of complexity for the simplest element. It's not just make it cold. It's make it cold and flip the spins.
It highlights just how unique hydrogen is. No other element gives us this specific headache.
So speaking of headaches, let's talk about how we actually get this stuff. We established it escapes Earth, so we have to make it. And right now we are mostly making it from the very thing we are trying to replace, right?
Unfortunately, yes. This is the reality of the colors of hydrogen you might hear about. Right now, the vast majority of hydrogen production is what we call gray hydrogen.
Gray hydrogen, which comes from fossil fuels.
Specifically, natural gas. We use a process called steam methane reforming, or SMR. We take methane, CH4, and blast it with high-temperature steam.
And that just rips the hydrogen off the carbon.
Exactly. You get hydrogen gas, but you also get carbon monoxide and, eventually, carbon dioxide.
How much CO2 are we talking about here?
It is significant. For every 1 ton of hydrogen you produce this way, you are generating between 6.6 and 9.3 tons of CO2.
Wow, so nearly 10 times the weight in pollution? That kind of defeats the purpose if you're trying to be green.
Which is why there is such a push for green hydrogen. This is the cleaner alternative, electrolysis.
This is the high school science experiment again. Stick 2 pencils in water, hook up a 9-volt battery.
On a much, much grander scale, yes. Use electricity to split water, H2O, into hydrogen and oxygen. If that electricity comes from renewable sources, wind, solar, then the hydrogen is effectively carbon-free.
So why aren't we doing this everywhere? What's the holdup?
Cost. It is much more expensive than steam reforming. And it requires expensive catalysts, usually platinum or iridium, though nickel is being used more. It is an economic battle right now.
But there are some weirder ways to make it, right? I saw biohydrogen in the notes. Are we talking about like hydrogen farms?
In a way, certain bacteria and algae naturally produce hydrogen. They have enzymes called hydrogenases.
Hydrogenases?
These enzymes allow them to essentially exhale hydrogen under certain conditions. There are even bacteria like Mycobacterium smegmatis that can survive by consuming the trace amounts of hydrogen in the air.
Wow.
So we are researching ways to harness these biological processes to produce hydrogen for us.
That's incredible. A bacteria breath powering a car. But there's another source that I think is the most provocative. We always assume we have to make hydrogen, but the outline mentions a geological surprise.
This is a very recent and exciting shift in geology. For a long time, the dogma was that pure hydrogen gas doesn't exist in the ground. We thought it was too reactive, that microbes would eat it or it would react with rocks.
But we were wrong.
We were. We are discovering natural geological processes, specifically something called serpentinization.
Serpentinization, great word. What is happening there?
It happens when water meets iron-rich rocks deep underground. The water oxidizes the iron, essentially rusting it, and in that chemical reaction, hydrogen gas is released.
So the Earth is naturally producing hydrogen factories underground.
Correct. And we have found large deposits. There is a famous one in Mali. There are findings in France and Australia. People are starting to use the term gold hydrogen or white hydrogen.
Like the gold rush?
Exactly. If we can tap into these natural reservoirs, it could completely change the equation. We wouldn't have to make it from dirty gas or expensive electricity. We could just drill for it, like we do for oil.
That sounds almost too good to be true.
Well, the economic extraction is still uncertain. We don't know how fast it replenishes or how easy it is to capture. But it challenges the assumption that hydrogen is just an energy carrier. It might be a primary energy source.
That is a massive distinction. Okay, so let's assume we have the hydrogen, whether we made it, grew it with bacteria, or drilled it out of a rock in Mali. What are we actually doing with it? Because I think most people hear hydrogen and they think cars.
Cars are the visible tip of the iceberg, but they are actually a tiny fraction of current use. If you want to know what hydrogen is really doing, look at your dinner plate.
My dinner plate.
Approximately 50% of the nitrogen in your body came from the Haber process.
The Haber process, this is for ammonia production.
Yes, the single biggest consumer of hydrogen today is the production of ammonia, NH3, for fertilizer. Without synthetic fertilizer, we simply could not support the global population.
So hydrogen is literally feeding the world.
It is the bridge between the nitrogen in the air and the food on our table. It is absolutely essential for modern agriculture.
That's high stakes. What else?
Well, the most glamorous use is rocket science.
Of course.
Liquid hydrogen is the fuel of choice for high-performance rockets. The space shuttle main engines, for example. When you mix liquid hydrogen and liquid oxygen, you get the highest specific impulse, the most bang for your buck in terms of thrust efficiency of any chemical rocket fuel.
And the exhaust is just steam.
Superheated steam, yes. Which brings us to the energy carrier role. Fuel cells.
This is the dream of the hydrogen economy.
A fuel cell creates electricity by combining hydrogen and oxygen, but instead of burning them in an explosion, it controls the reaction chemically. Electrons are stripped off the hydrogen, forced through a circuit to do work, like turning a motor, and then reunited with oxygen on the other side.
And again, the only emission is water vapor.
It is incredibly clean at the point of use. We're seeing this scale up in buses, trains, and potentially heavy shipping in aviation areas where batteries are just too heavy.
Right, because batteries are heavy. Hydrogen is light. If you need to fly a plane or push a cargo ship across the ocean, hydrogen or synthetic fuels made from it might be the only way to decarbonize.
There are also some really fascinating niche uses. For example, did you know hydrogen is used as a coolant in electrical generators?
A coolant, but it's flammable.
It is, which sounds counterintuitive.
Yeah.
But hydrogen has the highest thermal conductivity of any gas. It is incredibly good at moving heat away. And because it has such low density, it creates very little wind resistance or windage loss on the spinning rotors of the generator.
So giant power plants are cooling their generators with explosive gas because it's slippery and conducts heat well.
Precisely. They just have to be very careful to keep the air out so it doesn't ignite.
And I saw one other niche use that surprised me, the food industry. E949.
Yes. Hydrogen is an authorized food additive. It's used as a packaging gas.
A packaging gas.
It prevents oxidation. If you have fats or oils in the food, oxygen will make them go rancid. Hydrogen helps protect them. It's also used in the hydrogenation of fats, like making margarine, though that is a chemical reaction rather than just packaging.
It's everywhere. In the rockets, in the generator, in the fertilizer, in the margarine. But we have to talk about the dangers. We touched on the Hindenburg, but the safety reality check in the source material is fascinating. Specifically, the invisible danger.
This is something that terrifies people who work with pure hydrogen.
Yeah.
Hydrogen flames emit very little radiant heat, and, crucially, they emit light almost entirely in the ultraviolet range.
So, in daylight,
You cannot see the fire.
that is the stuff of nightmares. How do you even know it's there?
There are stories from the early days of hydrogen research where workers would walk around with a broom held out in front of them.
A broom.
If the bristles started burning, they knew there was a hydrogen leak and a fire right there.
The broomstick method of fire detection.
Low-tech, but effective. Nowadays, NASA and industry use specialized flame detectors that can see the UV and IR signatures. But imagine walking into a flame you can't see.
And it's not just the fire, it's what hydrogen does to the pipes holding it. Embrittlement.
This is a material science nightmare. Hydrogen atoms are so small that they can diffuse into the crystal lattice of solid metals like steel.
They just wiggle their way in between the iron atoms.
They do. And once they are inside, they create internal pressure. They can form little pockets of gas inside the metal, causing it to crack and shatter essentially from the inside out.
So you can't just put hydrogen in a regular natural gas pipeline.
Not easily. You need special coatings or specific alloys that are resistant to hydrogen attack. It makes the infrastructure challenge much harder than just switching the tap from gas to hydrogen.
And then finally, the explosivity. We know it burns, but the range is wide, isn't it?
Extremely wide. Gasoline fumes need a very specific ratio of air to burn. Hydrogen will burn in air at concentrations anywhere from 4% to 74%.
So almost any mixture is a bad mixture.
However, there is a saving grace. Remember how light it is.
It floats up.
Exactly. If you have a gasoline leak, the fumes pool on the ground, waiting for a spark. If you have a hydrogen leak outside, it rises and disperses into the atmosphere at 20 meters per second. It flies away from the danger zone very quickly.
So in a way, it's safer in an open crash than gasoline might be.
In an open environment, yes. In an enclosed space,
Yeah.
oh, that's a different story.
Okay, so let's try to summarize this deep dive. We have gone from the Big Bang, where hydrogen was born.
Yeah, to the inside of Jupiter where it turns into a metal. We've looked at the spin isomers that make storing it a huge headache.
We've discussed how we strip it from fossil fuels, how we split water to make it green.
And the tantalizing possibility of mining it directly from the Earth.
We've seen how it feeds the world through ammonia and powers rockets into orbit, and we've looked at the invisible flames and the cracking pipes.
It really is the element of everything. It is the beginning, and in many ways, it is the future.
So what's the final thought for the listener? What should they be thinking about when they turn this off?
I want to go back to that geological surprise. For centuries, we have viewed hydrogen as an industrial product, something we have to manufacture. But the discovery of natural gold hydrogen reserves challenges that fundamental assumption. Are we standing on top of a resource that could decarbonize the planet without the massive energy cost of electrolysis? Or will it remain elusive, slipping through the cracks in the earth, just like it slips through our fingers?
That is the trillion-dollar question. Is the gold hydrogen rush real?
And a final personal thought. The next time you drink a glass of water, just remember, you are drinking star fuel that is burned. You are drinking the ash of the cosmos.
I will never look at a glass of water the same way again. Thanks for listening to The Deep Dive. Stay curious.
Bye,